Hello, this is Jack Jackson. In this video, we're going to review several ideas from calculus, particularly in Calculus 3, and we're going to be talking about multivariable and vector calculus reviews. We're going to talk about some basic formulas real fast, and also about some big theorems from vector calculus. And we're just going to kind of do a very quick overview and review of many of the concepts from the course. First of all, we have talking about different types of functions, and the first line there is f of x is input's a single real number, a scalar, and the output is also a scalar, a single real number, and the graph is a curve in 2D. Well, that's the kind of functions that we mainly studied in Calculus 1 and most of Calculus 2 as well. Then we also have other kinds of functions. This may not be an exhaustive list of all the kinds, but we at least studied all these kinds of functions. We studied f of xy. The input was an ordered pair of real numbers and the output was a single real numbers. That graph was a surface in 3 dimensions. Or we could do f of xy z. That would be an ordered triple of real numbers for input, and output was a single real number. That's a solid region. In 4D would be a graph, which we don't really usually graph that. R of t, the vector function, the input's a single real number, a scalar, and the output's a 2D vector. That would be a curve in 2D. Or it might be a 3D version of that. The input's a single real number, and the output is a 3D vector. And the output is then a curve in 3D for the graph. So that's a position function. We looked at a parametric, so those are basically parametric equations. Then we looked at parametric equations where we had 2 parameters, r, position function as a function of, say, 2 parameters, say t and u. The input's an ordered pair of real numbers, the output's a 3D vector, and the graph there is a surface in 3D. We looked at vector functions, vector function f of xy, where the input's an ordered pair of real numbers, and the output is a 2D vector. And then the graph was a vector field, a whole bunch of vectors in 2 dimensions. We also have a vector function of xyz. That's the input's an ordered triple of numbers, and the output vector is a 3D vector, and the graph would be a vector field in 3D. And then these derivatives that we have, the regular derivative, the gradient, divergence, and curl, they themselves are all functions, but they have an input function and an output function. Not really a graph, but an input and output function. So when the derivative, that differential operator of taking a derivative of something, is itself a function which takes a function of one variable for input and gives you out a new function for the output, the derivative function. In Cal 3, we also extended that to talk about the gradient as a differential operator. That gradient is inputs a scalar function of perhaps multiple variables, and then a vector function is the output of the same number of variables. The divergence, we input a 3D vector function, we output a scalar function of 3 variables. And the curl, we input a 3D function, vector function, and the output's a 3D vector function. So we have all these different kinds of functions, and maybe a few more that we've studied in calculus. So one of the first things we did is we just kind of talked about what these kinds of functions are. We talked about limits, derivatives, and integrals, and how, and in the fundamental theorem of calculus, how do those things relate, and how are they extended, what stays the same, and what needs to change as we go into this. And that's basically what we studied in Calculus 3. So in multivariable and vector calculus, one of the most basic concepts is the derivative. Okay, and in multivariable and vector calculus, we encountered several analogs of the derivative that we studied back in single variable calculus. A derivative is a rate of change, and it's based on applying a limit to some average rate of change. The new versions of derivatives that we studied in Calculus 3 are all based upon the basic definition of a derivative that was introduced early in Calculus 1. So therefore, all the little shortcut formulas that we derived for computing derivatives in Calculus 1 can be applied in working with the various types of derivatives in Calculus 3, as long as we sort of know how that's extended. The following page is going to summarize some of the types of derivatives that we studied in calculus. With these, when these are evaluated at a specific point, the output is a single constant. Now that might be a scalar constant, single scalar, an ordered pair, real numbers. It might be an order triple, it might be a 2D or 3D vector, depending on what type of derivative we're talking about. But when you apply these for variable inputs, then we actually get functions for the output. And notice that the type of input function, the type of output function for each type of derivative is given on the following page. And it kind of lines up with some of the different kinds of functions we were looking at earlier. And notice there are derivatives for basically every kind of function that we've talked about all semester. So first we just have the basic derivative from Calculus 1. It's the instantaneous rate of change in the output with respect to the input. It's the slope of the graph at a particular point. In other words, it's the slope of the tangent line to the curve at a specific point. One of the first things we did when we started talking about derivatives in Calculus 3 is we talked about partial derivatives and then directional derivatives. They're slopes of the surface in a particular direction. In other words, they restrict the motion to one plane. They intersect the plane with the curve, with the graph, and it produces a curve. And then we find the derivative of that particular curve, and that's the directional derivative. The gradient is a scalar. The gradient's a vector. The partial derivatives and directional derivatives are scalars. But the gradient is a vector. Its direction is a direction of the greatest directional derivative, and its magnitude is the amount of that greatest directional derivative. So it's the way you want to go if you want to increase the fastest. And when we have a contour graph, the gradients will be perpendicular to the contours. A velocity is a vector derivative of a position function with respect to time. The magnitude of the velocity is the speed of the object in motion, and the direction of the velocity is the direction of the motion. And it's always going to be tangent to the curve that traces out the path of the motion of the particle. The divergence is the flux density of a smooth 3D vector field. It's the flux per volume at any point. And basically what we do is we take a sphere centered at the point, oriented outward, compute the total flux out of the sphere. Then we divide this by the volume of the sphere to obtain the flux per volume, a flux density. Finally, we take the limit as this volume of the sphere approaches zero to obtain the flux per volume at a single point, and that's the divergence of that point. Notice it is it's a scalar. Okay. The curl is a vector derivative. The divergence and curl, both of those take inputs of vector fields and output a type of derivative. The divergence is a scalar and the curl is a vector. And basically first on the curl we want to think of taking any vector, a normal vector, and take a closed curve around a point at the beginning of that vector that's in a plane perpendicular to that vector, and then it's oriented by the right-hand rule. And we find the circulation about that curve and divide it by the area of the region bounded by the curve. So that gives you sort of a circulation density. And then we take the limit of this as the area inside the curve approaches zero, so you sort of lasso this thing and then pull it tight, to find the circulation density at the point about the vector. And that's going to give you a circulation density about a particular, say, normal vector. Okay, then what if we take this point and there's all these different normal vectors we can go. Whichever one of those has the biggest circulation density, pick that one and take its magnitude as the curl and its direction as the direction of the curl. Now, these are the most important things, the actual physical interpretations, but we also have algebraic definitions as well. And so they're summarized on this page. And the derivative, it's a scalar function of one variable for an input, and the output is a scalar function of one variable. Again, thinking of this as a variable x. And of course, f prime of x is df over dx is defined to be the limit as h goes to 0 of f of x plus h minus f of x over h. A partial derivative and directional derivatives, they're scalar functions of multiple variables for the input, and the output is a scalar function of multiple variables. So f sub x, or df, the partial derivative of f with respect to x, is the limit as h goes to 0 of f of x plus h, comma y, comma z, minus f of x, y, z over h. And similarly, we could define in a similar way the partial derivatives with respect to y and z. And we can use those, actually we use the gradient down here, to get our idea at a directional derivative in some other direction besides just say the x or y or z axis directions. The gradient is takes a scalar function of multiple variables, say 3 variables, and the output is a vector function of multiple variables, and you do it by just sort of a scalar multiplication of this del operator across here. In other words, you just distribute the del operator across each of the component functions where this is a del operator. In other words, what I'm saying is you just take the derivative of each piece, but what you're doing is you're taking the derivative of the first component with respect to x, the second component with respect to y, and the third component with respect to z, and put those into a vector form. The velocity is a vector function of a scalar parameter for the input, and the output is a vector function of a scalar parameter. So we take a position function, r of t is x of t, y of t, z of t, and we do again do that del of r, or v of t, or r prime of t, and you just take the derivative of each piece, this time with respect to t. The divergence is a type of derivative that we have a vector function of multiple variables and the input, and the output is a scalar function of multiple variables. This time you take the del operator and dot product it with f, and the way that basically works is if you have the divergence of a function here, we take the partial derivative of the first part with respect to x, the partial derivative of the second part with respect to y, and partial derivative of the third part with respect to z, and then add those up. It's basically the same thing as just adding up the 3 components then that you get. I'm sorry, it's not. This is starting with the vector function. It's doing 3 derivatives like we did on the gradient, but the gradient you had a single function f here that you're finding, and down here we have a vector function with 3 components. Now the curl, we have a vector function of multiple variables for the input and a vector function of multiple variables for the output. So it's this del operator cross with f, which you can use this to help you remember it, but it's basically this formula here is the formula for doing the curl. One of the things that we studied was motion, and we had a vector position function r of t that gives the location of a point as a displacement vector from the origin in terms of the parameter t. And if we interpret t as time, then t is time, the position is r of t, which is given in component form there, or parametric equations that gives you the x, y, and z as functions of t. The velocity is the r prime, just take the derivative of each part. The acceleration is the derivative of the velocity, or second derivative of the r. The speed is the magnitude of the velocity. A unit tangent vector would be the velocity divided by its norm, because the velocity is always tangent to the curve. We just have to divide by its norm to make it a unit tangent. The arc length of a curve is just integrate is s, and you just integrate ds to that. Well, another way to get ds is the norm of the velocity dt. So that's the square root of x prime squared plus y prime squared plus z prime squared. Take the square root of all that, integrate with respect to t from the first to the beginning to the ending t. And here are some formulas for putting a projectile with constant acceleration in motion. Now we also had integrals as well as derivatives. So in multivariable and vector calculus, we encountered several types of integrals, and they're all based upon the limit of some type of Riemann sum. And ultimately, they are basically based on the definite integral of a real valued function, a real variable, that we studied back in Calculus 1 and 2. So the basic integral we did in Calculus 1 and 2 is the net signed area between a curve and the x-axis. We divide the domain interval into subintervals and multiply the width of the subinterval by an x value, by a y value of some x value in the subinterval to obtain the area of a rectangle. So we're multiplying the width of the subinterval by y value corresponding to an x value in the subinterval to determine an area of a rectangle. Sum these areas. Take a limit as a Riemann sum as the number of subintervals goes to infinity and their widths go to 0. And so there is the definite integral. Well, in this semester we studied double integrals, triple integrals. In a double integral, we take a rectangular region, x going from a to b and y going from c to d, and make sure it's big enough to include the domain of some function f of x, y. Define a function g of x, y to be identical with f on the domain of f, but 0 otherwise. Divide the rectangular region into rectangular subregions of area delta a sub k, and evaluate the function at some point in the subregion, multiply by the area, to obtain a volume of rectangular prisms. Sum these volumes, and take a limit as the number of the subrectangles approaches infinity, and their areas approach 0, and we have a double integral. And it turns out to be equivalent to iterating two single integrals. Similarly, for a triple integral, we take a rectangular region, this time not a rectangle, but like a prism. Okay, so it's x going from a to b, y going from c to d, z going from h to I. And make sure it's big enough to include the domain of our function f of x, y, z. Let g of x, y, z be a function identical with f on the domain of f and 0 otherwise. Divide the rectangular solid into rectangular regions of volume delta v. Evaluate the function at some point in the subregion and the function g in that subregion, and multiply by the area to obtain the volume, hypervolume of a multiply by the volume, that should say. So this gives us some sort of fourth dimensional hypervolume of these hyperprisms. Sum those and take a limit as the number of subprisms approaches infinity and their volumes approach 0. And that's equivalent to iterating three single integrals. And when we get to vector calculus, we introduce some new even further integrals. We have the integral of a vector function of one real variable, so f of t, and you just integrate with respect to t, then you're just integrating each component wise. We can do that. We can also have a line integral of a scalar field over a 2D curve. So a line integral of a scalar field ds is, or it can be written with or without this little circle thing, but it's defined to be the limit as n goes to infinity and delta s sub k approaches 0, the sum of f of x k y k delta s. It's a net signed area between the curve and the xy plane. And then you can extend that to a line integral of a scalar field over a 3D curve in a very straightforward way like this. The line integral over a vector field measures the contribution of the vector field in the direction of the velocity, in the direction of motion along the curve. And so we write that as the line integral over the curve of the vector f dot d vector r. And that's the limit as n goes to infinity and these delta r sub k vectors approach 0, either approach the 0 vector or the norm of them approach 0, and of the f sub k dot the delta r sub k. And we work that out by parameterizing it from a parameter from the beginning into the end of the curve from t1 to t2, and you write that f of the r of t, so they ultimately get an f of t dot with the r prime and then dt. We have surface or flux integrals, and there's various kinds of those. So the flux integral of a scalar function, just like you had a line integral of a scalar function, you can have a flux integral of a scalar function. And so z is a function of x and y, then the flux integral of that ds can be done this way. It's f of xy and then g of xy for z. And then the ds is g sub x squared plus g sub y squared plus 1 square root, and then you've got your dA, which is dy dx. You can add your flux integral of a scalar function for over a surface is given parametrically. Okay, and what we get there is, this is again for a scalar function. We get f of x, y, z given in terms of s and t. So write your scalar function in terms of, say, parameters s and t. And then you take r sub s, that vector, cross product with the r sub t vector. Those are partial derivatives there. Cross product, do that norm, and then you have ds dt. If you want the flux of integral upward with a vector function given by z as a f of xy, then this equation will show you how to do that. If the flux integral of a vector function over a right circular cylinder centered on the z-axis and oriented outward, here's how that parameterization works out. The flux integral of a vector function, again, measures the flux or flow out of the vector field through the surface. So if we have a vector S over a sphere centered at the origin, this is what it turns out to be. And in more general, most of the ones that I've done here in the notes so far are a flux integral of a vector function over a surface given parametrically in terms of parameters s and t. And here is how you can set that one up. So summary of those formulas. We also have different coordinate systems where we can have rectangular, cylindrical, and spherical coordinates. So rectangular, we're given a point by an x, y, and z coordinates. Cylindrical, we're given r, theta, and z. And spherical, we're given rho and a theta and a phi. And we have some basic relationships. Cosine of theta is x over r. Sine of theta is y over r. Tangent theta is y over x. Cosine of phi is z over rho. Sine of phi is r over rho. X squared plus y squared is r squared, and x squared plus y squared plus z squared equals rho squared. And so solving these around, you can substitute and change things out for changing variables. But this dv is dz dy dx is also r dz dr d theta, or rho squared sine of phi d rho d phi d theta. So you have to be sure you take care of the dv as well when you're changing coordinate systems. Now we have we talk about derivatives and integrals. Then the next thing is how they connect, and they connect with the fundamental theorem of calculus. And so we have a few theorems in vector calculus which are similar to the fundamental theorem of calculus from single variable calculus. In each case, we will see that we could rewrite an integral of a derivative function over a domain as an integral of its antiderivative function over the boundary of the domain. And notice that this reduces the dimension of the integral by 1. Of course, if the original integral is 1, the zero-dimensional analog of the integral is simply evaluating at the endpoints and subtracting, finding the length of that interval. So the fundamental theorem of calculus, at least the part we're going to be talking about now, says if we're finding the definite integral of the derivative of a function, then we simply find the amount of change in the function, the antiderivative of the given integrand, like this. So the integral from a to b of f prime of x dx is f of x evaluated from a to b, or f of b minus f of a. So the fundamental theorem of line integrals basically works the same way. If the vector field is the gradient, a type of derivative, of some potential function f is kind of the type of antiderivative of what we start with, then we can calculate the line integral over the curve by evaluating the potential function at the two endpoints and subtracting. And notice that if it is a gradient field, this makes it integral independent of path. Stokes theorem is a similar version of the fundamental theorem of calculus. The surface integral of the curl of a vector field over an oriented surface is interchangeable with the line integral of the vector field over the boundary curve. And notice that when a parameterization is applied, this ultimately interchanges a double integral over the surface with a single integral over the parameterized boundary curve. Of course, this equality works both directions. So basically, this gives you two ways to set up this integral, either as a line integral or a surface integral. We work whichever one's easier for you. Green's theorem is basically just Stokes theorem restricted to a plane. So if you notice, the right side is exactly the same here and here, but this side here becomes this side here in terms of once you work this out for 2 dimensions, because R is an open region with a piecewise smooth simple closed curve as its boundary, and the direction around the curve is such that R is always to the left of C, so that the normal vector will point out of the plane. And F is a smooth vector field on the open region containing R and C. Then this left side of Stokes' theorem becomes, this dot product right here basically becomes just this scalar version of the curl and times the dA. And then, of course, that's going to reduce to a double integral there. So that's a double integral on this side. And if we parameterize, that's a single integral on this side. In both cases, it's a double integral on the left and a single integral on the right once we introduce parameters. The divergence theorem. The integral of the divergence of a vector field over a 3D region is interchangeable with the surface integral of the vector field over the boundary surface. And notice that when the parameterization is applied, this ultimately interchanges a triple integral with a double integral. So let W be a solid 3D region, and let S be the surface, which is the boundary of W, and S needs to be piecewise smooth and oriented outward, and the vector field needs to be defined everywhere on W, including the boundary. Back on the previous one, we also needed the vector field for Stokes' theorem and Green's theorem. The vector field has to be defined on both the boundary and all the points inside the area of the surface. Here we have a solid region W. We take the divergence of F, and if we're integrating that, then we can just get the flux integral out of the surface that's the boundary. So you can do that either way, set up whichever one is the easiest to work and work that out. So that's a quick overview of lots of stuff that we did in Calculus 3, and hopefully sort of get the sort of a lot of formulas here that you can look at for reference, but also we're trying to get the sort of the bird's eye view, the big picture, so that we see the forest of what's going on, of some of the basic things and how they connect together, along with some formulas and stuff for some of the details. So hopefully that was a nice little quick overview and review of a whole bunch of Calculus 3.